By knowing K, that is, the value of the equilibrium constant, and the amounts of reactants and products at any particular time, we can predict which way a reaction will proceed. In other words, we can predict which rate, either the reverse or the forward, will predominate until we eventually reach equilibrium. This involves something called the reaction quotient, which we symbolize by capital Q. And the reaction quotient is the number that you get when you plug the reactant and product amounts at any given time into the equilibrium constant expression. In other words, when you have the product amounts and the reactant amounts at equilibrium, you get a value, and that value is K. When you have the product and reactant amounts at some other time, if you put products to their powers divided by reactants to their powers, you'll get a different value typically. And we call that value Q, the reaction quotient. And depending on how Q compares in magnitude to K, we can predict which way the reaction is going to proceed, which rate, either the forward or reverse, will predominate until we eventually reach equilibrium. Down in the lower left here, if Q is larger than K, let's look at Q. If Q is larger, that means that there are more products in the system than there should be at equilibrium. And if you have too many products, that means that the reaction needs to proceed to the left. In other words, the reverse reaction will predominate. If we go to the next point, if Q is smaller than K, again, look at the fractions here, 2/3 of the way down the page, where it has the K and the Q. If Q is smaller than K, that must mean that we don't have enough products compared to what we should have at equilibrium. And if we don't have enough products, we better make more. The forward reaction rate will be higher than the reverse reaction rate. If we plug in some numbers at some particular time and we get a value that is actually equal to K, then we know, oh, okay, I guess we're at equilibrium. Let's try an example. For this reaction, K sub C is equal to 51 at a temperature of 488 degrees Celsius. We start with a certain amount of each of these substances in a 2-liter container. Which way will the reaction proceed? So what we're going to do is we're going to calculate a value of Q. And the way we do that is to write an equilibrium constant expression. And we put in the values of concentration. Concentration is moles divided by liters. And since we're given moles and we're given liters, I've put that into this equilibrium constant expression. And this is the number that pops out, 1.3. In other words, at this instant, the value of the reaction quotient is 1.3. Now, how does that compare to the equilibrium constant? Well, the value of the equilibrium constant is 51. In other words, we need to make more product before we get to equilibrium. So the reaction is going to proceed to the right. That is, the forward reaction is going to predominate over the reverse reaction at this instant. Let's summarize the reaction quotient. The reaction quotient Q is found using the same equilibrium constant expression we use with a K. The difference is this. If we use the equilibrium constant expression when all reactants and products have equilibrium concentrations, then the number that emerges is the value of K. If we use amounts of reactants and products at any old whenever time, we will get a value for Q. Obviously, there are many possible values for Q, as amounts of reactants and products vary over time and between one experimental setup and another. At a given temperature, there is only one value of K. If Q is less than K, the forward reaction is favored. If Q is greater than K, the reverse reaction is favored. Q is equal to K, the system just happens to be in a state of equilibrium.